Okay, our next speaker, we're going to talk about the HamSCI Personal Space Weather System Magnetometer project. The Magnetometer project is probably less known than some of our shortwave and HF projects, but I think between the Grape 2 coming out and the new magnetometer boards we have for it, the magnetometers that are available in the Tapper store, and with today's talk, hopefully we can raise the profile of the magnetometer a little bit, get more of them installed, and expand that network. So I'd like to introduce Joseph Visone from the New Jersey Institute of Technology.
Hello, can you guys hear me? All right, good morning, everyone. My name is Joseph Visone. I'm currently an undergrad research assistant at the New Jersey Institute of Technology, and I'm currently studying applied physics. I'll be talking about the magnetometer and the Personal Space Weather Station, which I'll be referring to as the HamSCI Mag. And the contents of this presentation were contributed to by Hyomin Kim, David Witten, Julius Mady, Nathaniel Frizzell, John Gibbons, Bill Engelke, Anderson Little, Nicholas Muscoliono, and Xiaoshu Chao. In the Personal Space Weather Station, the HamSCI Mag's purpose is to provide a general context of geomagnetic activity during HF experiments proposed by the Personal Space Weather Project, mainly dealing with the Grape 1. HF communication is affected by ionospheric conditions, which are inarguably associated with solar and geomagnetic activity. And magnetic field observations from the HamSCI Mag provide critical information about such an interaction. And the magnetometer plays a key role in many space weather-related investigations, giving us information about ionospheric current systems and magnetic field disturbances by measuring magnetic field variations in nanotesla over time. And with the HamSCI Mag and the Grape paired, it will allow us to estimate ionospheric currents at mid to high latitudes. And during geomagnetic storms and substorms, the magnetic field variations can range from tens to hundreds of nanotesla, which is easily observed by the magnetometer, which has a field resolution of around 3 nanotesla. And one major purpose of inclusion of the HamSCI Mag is to increase spatial resolution of magnetic field measurements at mid to high latitudes, primarily in northern North America, around Canada and Alaska. And the proposed densely spaced magnetometer network can also provide a complementary data set to help infer ionospheric currents over the entire region where the Personal Space Weather Station is located. Ideally, the magnetometers and the Personal Space Weather Stations as a whole would be placed around 50 to 100 miles apart from each other. And such a citizen science level, large-scale, densely spaced magnetic field observations have never been conducted before. There are still many unsolved questions as to how the magnetosphere and ionosphere respond to solar activity, particularly in greater detail in terms of spatial scale. The RMF 3100 uses PNI Corporation's magnetoinductive technology to measure 3-axis magnetic field variations with a resolution of around 3 nanotesla at a 1 Hertz sample rate. And given that the magnetometer will be placed in a variety of electromagnetic environments, the field resolution could be a little larger than 3 nanotesla, though, as I previously mentioned, given that major geomagnetic events are on the order of tens to hundreds of nanotesla, it will work just fine in a variety of these environments. And all these events are still expected to be observed. And though the performance level of the HamSCI Mag is lower than that of a professional science-grade magnetometer, the price point of it is around 250 USD for the full setup, as opposed to thousands to tens of thousands of USD. And this is the full magnetometer set. Point A refers to the Raspberry Pi single board computer. Part B refers to the local board extender. C refers to the Cat5e or Cat6a cable, which connects the local and remote boards. D refers to the remote board extender, which directly connects to E, which is the RMF 3100 magnetometer. And the image on the right shows the housing of the remote magnetometer board, which would be buried. And that red dotted line refers to where the remote board will be placed in that PVC tube, which would be at the bottom of where it would be buried. So that dotted circle would be placed at the bottom in the ground. As previously mentioned, the magnetometer consists of the sensor and the host computer, which is the Raspberry Pi. The sensor and housing should be placed away from any electromagnetic interference sources that may affect the recorded measurements. And as written here, the best practice is to locate the sensor outside the building with the Raspberry Pi with a minimum length of 100 feet. But the Cat5a and 6e cables can go upwards of 300 to 500 feet. But yeah, and ideally just placed away from the house with the host computer. And this is a photo of the fully deployed remote sensor board. And the housing should be placed vertically, leaving about 10 inches of the upper part above the ground surface. And the sensor should be oriented with the widely accepted geomagnetic coordinate system, HEZ, where H points in the direction of geomagnetic north, not geographic north, geomagnetic north. E points in the direction of geomagnetic east, and Z points down into the center of the Earth, forming a fully orthogonal system. And this figure shows a comparison of 4 science grade magnetometers, the ones in Iqaluit and Ottawa, run by the National Resources Canada, and the ones in Boulder and Fredericksburg, run by the US Geological Survey. And the bottom 3 in Hope, New Jersey, Scranton, and Columbia are all HamSCI mags. And as you can see around 3 UTC, all of them show a consistent reading on an event taking place on March 31st of 2022. They all show that same spike. And Iqaluit has a much more scattered measurements, as it's at a very high latitude where the magnetic field is much more sensitive to any disturbances. And over the next couple slides, I will look at an event, a geomagnetic storm on April 10th of 2022. This figure shows measurements taken from satellite data from NASA's Omni instrumentation. From top to bottom, the plots are the BZ magnetic field component, the flow speed, flow pressure, and the SIM-H index. And around 3 UTC on this plot also, you can see a major spike in pressure, which is also reflected on the BZ component and SIM-H index. And because this is in a satellite, the readings that we see in this plot will come a little earlier than the readings on a personal space weather station, which is showed here. The top plot shows the Doppler shift of the WWV signal from a Grapevine. And this personal space weather station is located in Scranton, Pennsylvania. The second plot shows the magnetic field variation measured from a HamSCI mag with the BX, BY, and BZ components related to the HEZ components that I mentioned before. And the bottom plot shows a Fourier transform spectrogram of the second plot. And throughout all these, you can see at around 4:30 to 5 UTC, you can see this major spike in the magnetic field in the second plot, which is also reflected in the Doppler shift going below -1 Hertz in the grape plot. And it's also reflected in the spectrogram with the wave activity around 1 to 2 millihertz. And as I mentioned before, a big benefit to this project is the spatial resolution of measurements that we will develop. In this little GIF of supermag magnetometers, you can see that in North America, which is on the bottom left of the top right plot, there's not very many measurements compared to Europe, where you see the really thick cluster of measurements. And all the green dots at the ends of the arrows are the locations of each magnetometer. And you can see in North America, there's not many. So having a much greater spatial resolution would be of much benefit. And the bottom left plot shows a vector plot of the event we were just talking about. Both these plots are also from April 10th of 2022, where the bottom left plot shows 0 to 12 UTC, and the top right is a little video going from 440 UTC to 520 UTC, which is right where this big spike is observed on the ground instruments. And you can see on the bottom left plot the major direction change from right around the time that our substorm event is observed. Because all of these plots are from the substorm event, which is the result of the geomagnetic storm from this, because you can't see it on the supermag plot, but North America is on the nighttime side of Earth, so they experience the end reaction of the storm event, which is why it's much more delayed from the Omni data. And just to conclude with some key points, the HamSCI magnetometer in the Personal Space Weather Station will help increase the spatial resolution for observations of geomagnetic activity, whether that's geomagnetic storms, substorms, or large-scale ULF waves. And with 3-axis measurements, HEZ components, and a field resolution of about 3 nanotesla at 1 Hertz sample rate, the HamSCI magnetometer's performance is very adequate for any form of scientific investigations. And I'd like to thank the NSF and University of Scranton and everyone at NJIT and the HamSCI community. Thank you very much. And we're good. All right.
All right, Joseph, thank you very much. Well, that concludes oral session 1 on the Personal Space Weather Station. And if anybody's interested, it is coffee break time, I believe, for how long, Nathaniel?